Now in this part, we discuss the comparison of electric and magnetic forces. In electrostatics, we studied that if Q1 and Q2 separated by a distance r, the force Fe will be equal to 1 by 4 pi epsilon 0 into Q1 into Q2 by r square. Yes? Now if I treat the same thing in magnetostatics, and if I consider the case that two parallel wires carrying currents, if I consider one, two, current I1 and current I2, and the separation is again R, then there will be a force of attraction between these two infinite length conductors carrying current we studied, and that current attraction force, I take it as the magnetic force between them, and I consider a very small length element dl over here, dl1, and here also I consider a length element dl2. Now what is the force between these length elements if I assume that force Fm will be equal to mu 0 by 4 pi into I1 dl1 into I2 dl2 divided by r square. Now this formula is new to you because here this IL dl1, as per Bio and Savard rule, this is called the pole strength of the first part, and this is the pole strength equivalent of the second part. So pole strength of the first part and pole strength of the second multiplicate the two divided by distance square, you can get that magnetic force between them. This is according to magnetostatics. Then, if I take Fm in this form, and if I want to compare this with the first one, I'll be taking that formula rewritten as mu 0 by 4 pi into I1, I can take it as Q1 into V1, and I2 I can take it as Q2 into V2 divided by r square. This like this, that I into dl will be equal to Q by T into dl, and Q by T into dl, I can take the dl by T like this, and this can be integrated with what? Q into the velocity of motion of the charge particle through the conductor. Now here V1 and V2 are nothing but the drift velocities of the charge carriers in the conductors. V1 and V2 are drift velocities. Now you can compare Fa and Fm. Now when you compare that Fa and Fm from these 1 and 3, we get, see this one, drift velocities. And if I take that Fe by Fm from that, I will be getting Fe by Fm equal to, how much I get? Or let us take Fm by Fe. Okay, let us take Fm by Fe. if I take, you can see R square, then Q1 and Q2, all these are going, and finally I get here 4 pi and 4 pi goes. So I will be getting mu 0 into epsilon 0 into V1 into V2 divided by, V1 into V2. This is what I am putting. Fn by Fe equal to mu 0 into epsilon 0 into V1 into V2 I get. Now, mu 0 into epsilon 0, if I take, you studied that c, the speed of light is equal to 1 by root of mu 0 into epsilon 0. Electromagnetic theory of light, it says that the speed of light in vacuum can be taken as like this. It's a proven fact. Now when I assume this over here, what happens is that c square when I take, c square if I take, I will be getting this value, root is going, and you will be getting like this. So mu 0 epsilon 0 is equal to 1 by c square, and from this you get Fm by Fe. This is equal to V1 into V2 divided by c square. This is the thing you are getting. Now at this point we can compare the two forces. So we started from electrostatics and compared with the magnetostatic, and electric and magnetic forces are getting it equal to like this. Now let us assume the values to compare. The drift velocities V1 and V2 for the conductors. V1 is equal to V2 almost equal to 10 raised to minus 5 meter per second, approximately. Approximately it is coming like this, such a small speed. And speed of light, you all know that speed of light is equal to 3 into 10 to the power 8 meter per second. So, when I take V1 into V2 by c square, assuming these values over here, you will be getting Fm by Fe is very, very small compared to 1. That is, Fm by Fe is very much less than 1. This is very, very small value you are getting. That means that the force due to magnetism will be much less than force due to electric. If this is the condition you are getting, that is, magnetic force is very, very small compared to what? The electric force. But here comes the problem again. A question will be there, right? Even though the magnetic force is very, very small compared to the electric force, in the case of parallel wires carrying current, effectively no electric force is being seen between the conductors. What is the reason? Though both are having current flowing through it, but no electric effect is being seen. Now the reason for that is simple. First point is that why electric force is not prominent is that a current carrying conductor is not charged. Even though the current is flowing through the conductors, the charge neutrality is being considered there, or charge neutrality is not getting affected there. So effectively the conductors are not getting charged, and therefore the electric force is not existing between them. Now, magnetic force is very prominent in this case because here we are getting that magnetic force is very, very small. But when you take the case of parallel wires carrying current, that magnetic force is what? Very great between them. The fact is that the magnetic force is due to the charge moving through a magnetic field. That is magnetic Lorentz force. And the current carrying conductors are having large number of free electrons. So each moving charge is contributing to the magnetic force and they are getting added up according to the number. So as the number of charge carriers are very large and therefore effectively the magnetic force also becomes very large. So this is the fact by which the magnetic effect is found to be very great, greater compared to electric effect in this case, even though the magnetic force is very small compared to the electric force. Okay, this is very, very important, maybe a higher order thinking question. Okay, so take it seriously, understand it properly. Okay.